Okay, so I said this previously, but just to really reinforce it, a new variable will only be created if you have an equal sign in your expression. So if you run a statement and there's no equal sign, all it's going to do is save the result of your expression in the ANS variable. When you're writing lots of code, I wouldn't encourage you to make liberal use of the ANS variable. It's good to be aware of what your values are and store them in appropriate variables. So rather than in a piece of code writing square root of 25 and then using ANS equals and playing with the ANS variable, it's better to do x equals the square root like this and create a variable so that you can manage your own variables. So anytime you see a line with that equal sign in, we are creating a variable name. We're creating a variable with the name that is on the left of the equal sign and giving it the value that is on the right of the equal sign. And if the variable already exists, it will update that value. So we update variables and create new variables in exactly the same way. The only difference is going to be whether the variable is there or not. Okay, so you can do multiple assignments on a single line. This is only useful really at the very start of your code when you're defining a bunch of variables that you might use throughout the rest of your code. I wouldn't encourage you to combine too many lines using semicolons as a separator. It can get messy and it just improves readability if you put something on each line. But what you might do is inherit code from other people and not notice that there's extra commands hidden after a semicolon on the far right-hand side of the screen. It does happen. So in this first line, you'll see I've written a equals 4, b equals 2, and c equals a multiplied by b. I've separated my commands with a semicolon. However, you'll notice that the last line, the very end of the statement, doesn't have a semicolon, which is why c equals 8 is shown on the screen. If you define multiple commands on a single line separated by a semicolon, it's going to work from left to right. So here it's setting a equals 4, then it's setting b equals 2, and then it's doing c equals a multiplied by b. If you want to know what variables are defined in your current workspace, you can type who. I don't really use that much because I can just glance down at the bottom left of my window and see the variables that are defined. But who is the coding way of seeing the same thing. And we see that in my current workspace I have a, b, c, and x through z. And the ANS variable will be defined because I've ran some statements without equal signs. Whose is very similar to who, but gives you a little more information about the variables that you've defined. For example, here's when you would find out what precision is being used, what class the MATLAB has interpreted your variables as. And it also gives some interesting information that shows us sort of how MATLAB is thinking. If I type whose, I can see the name of the variables that I have defined. These names will be exactly the same as if I typed who, where it said what my variables were. If I type whose, it will tell me the size of the variable. So here's when we begin to see that MATLAB thinks of everything as a matrix, and everything is defined as a something by something matrix. So a single number, for example, a, is a 1 by 1 matrix. And so all these variables that I've defined are 1 by 1 matrices because they're just standard numbers. You won't need to worry about that. That might sound like, well, maybe MATLAB's not for me because I'm not going to be working with matrices, but it works just as fine with single numbers and lists, the same as everything else. It just happens that under the hood, MATLAB is thinking of everything as a matrix. Then it will tell you some information about how much memory is used to store these things and what class they are. You shouldn't need to worry about this as you get started. If you find yourself working with huge data sets and running out of memory, we can begin to manipulate these and make sure that we're using appropriate data types for all our data. Clear is very useful for taking a variable out of your workspace and deleting it. So if you see we had a defined in our workspace when we typed whose, if I then do clear a and type whose again, I see a list of my variables, but a is no longer there. Often when you write a script, if you don't want it to be interfered with by previous people's code or previous things that you've run, you might want to start your script with clear, which will clear all of the variables from your workspace. Alternatively, you can type clear space all, which will also clear all of the variables out of your workspace. So if you want to make sure when you run a script that nothing that was defined previously is carrying over and perhaps messing with your code, you can clear at the start. Then type whose again, and you should see there's nothing there. So the format command is useful when you're working with numbers and you're finding that it's giving you too much precision or too little precision, or you just generally want to display your numbers in a different way. So if I'm working with MATLAB by default and I check the value of pi, you probably see something that looks like this. So if I type x equals pi, I didn't put a semicolon at the end of my line, so it's showing me what value x has, and it's giving me pi to a few decimal places. If I want more precision displayed to the screen, I can type format space long, and then do the same command again. Again, there's no semicolon at the end of this line, which is why we're seeing all the information printed to the screen. And it's showing me pi to more decimal places. You can do format short to get back to this default, where it just displays a few. Short is the default, at least in my version. Bank is useful, obviously, when you're working with currency. People do use it also when they're working with biological data, because sometimes 2 decimal places is more than enough with the degree of precision of many of these experiments. And I'll show you how to do some more customizing of specific numbers of decimal places as we get towards print statements. The rat will attempt to show it as a rational fraction, make an approximation at that anyway. We don't use that much. So format short is the default and probably the most useful. It gives you a nice amount of precision. So as I mentioned previously when we looked at the whos command, numbers are actually one-by-one matrices. This seems like unnecessary complication, but actually it makes things really easy when you go on to work with multiple data points. Normally we're working with multiple data points. It might be a time course, it might be replicates, it can be a list of genes. Whatever it is, you're often doing something repeatedly for multiple bits of data, and you're doing the same thing to each bit of data. And so the fact that MATLAB presumes everything as a matrix makes that really easy. So if I check, this size command is something you need to become familiar with. If I check the size of x, which is this pi variable I just defined, you should see that it's 1 by 1. MATLAB always defines variables down then across. So if you see 1 by 1, it's telling you it's 1 down and then 1 across. So if I had something that was a different shape, like a matrix such as 1, 2, 3, 4, 5, 6, and I did the size of that matrix, it would tell me that it is 3 down and 2 across, and the result I would get back is 3 and then 2, rather than the 1 and then 1 that we see here. So it's always going to be down and then across. So to define a vector, you can think of these as lists if you've programmed in other languages before and you prefer to think that way. You put them in a square bracket and separate them by a comma. In MATLAB, you can also separate by a space. I like to get in the habit of separating by commas because it makes things much clearer and you're not worrying about the size of particular spaces. So if I define a variable called row vector, remember we create a variable if we have it on the left of an equal sign. I'm going to set that variable equal to some vector, so I've got square brackets, 1, 2, 3, 4, 5. A vector is just a one-dimensional matrix. It means I have a list of numbers rather than a list in multiple dimensions. And then I can, because I didn't finish my line with a semicolon, I see the results printed back, that those 5 numbers are in my row vector. Now there's a shorthand in MATLAB to do this. If you do 1, 5, it's going to automatically define all the numbers between 1 and 5. So an alternative to doing 1, 2, 3 all the way up to 5 is to do row vector equals 1, 5, and it automatically fills all the numbers between the 2 limits you defined. There's some more complicated examples of this that we'll come across later, but you can define some pretty, most of the lists you need to use you can define with colon notation. You won't find yourself typing out more than a few numbers separated by commas as you're defining lists. This is about as big as it'll have to be without using colon notation. So if I check the size of my row vector, it's telling me it's 1 down and 5 across, which makes sense. Here we see it. It's not got any depth. It's got a single entry vertically and 5 entries horizontally, which is why the answer to the size query is 1, 5. Notice it's defining this size into the answer variable because I didn't put an equals when I ran size. If I had done my size equals the size of row vector, it would have not put it in the answer variable, it would have stored it in the my size variable. But if you just briefly want to check the size of a variable, you can type size, put the name of the variable in the brackets, and it will show you how big it is. Can everyone see why this row vector variable that we've created is returning 1 and then 5 when we do size? So lots of those operations that we've already seen, like addition and subtraction, also define not just to single numbers, but to entire matrices. MATLAB doesn't differentiate between the two. So if I have this row vector, just checking what the value of the variable is. Remember, at any point you can check the value of a variable by typing the variable name and hitting enter. This is telling me that my row vector contains those 5 numbers. I'm going to define a second vector, which I've called second vector, and I'm setting it equal to 43210. Remember, they're in square brackets and separated by commas. I didn't put a semicolon at the end of that line, so the results are shown on the screen. I can then do one variable plus another variable, and it will, element-wise, one by one, add those 2 numbers together. So it'll do the first element of our row vector plus the first element of our second vector and put that in the first position of our result vector. So 1 plus 4 is going to be 5. And then we're going to do 2 plus 3, and that's also 5. 3 plus 2, that's also 5. So it's going to go through element-wise, one by one, adding the elements at the respective positions of our 2 vectors together and storing them in whatever our output is. Now for this example, I didn't put an equal sign on this line. There's no variable defined, so what it's doing is it's storing the answer in the answer variable. Okay, so everything we've been working with so far has been a vector going from left to right. It's been a matrix that has 1 down and a bunch across. Now we can also define column vectors. So those are vectors that go down rather than across. And the difference is we're going to separate our numbers with a semicolon. So in MATLAB, a comma means on the same line, and a semicolon means on the next line of our matrix. So here I'm defining a column vector equal to 1, and then in the next row 2, and then in the next row 3, then in the next row 4. And when I hit enter at the end of that line, what I see is the numbers printed down the screen rather than across. So now I have 2 vectors. I have a column vector and I have a row vector. And you might think, great, I want to add those 2 together. And what you'll find is that MATLAB actually returns an error when you try and do that because the dimensions don't agree. What it's trying to do is add the element at 1, 1, position 1, 1, which will be 1 down and 1 across, with the element at 1, 1 in the other matrix, which is fine because they both exist. But then it will get to 1, 2 and find that only one of them has a 1, 2. That's the row vector, whereas the column vector doesn't have a 1, 2 because it's going down the screen, and it struggles because the matrix dimensions don't agree. Now, for some operators, it would be fine with this. You know, you can do matrix multiplication and stuff on matrices that are different sizes. But for now, if you're adding things together, make sure you're aware that they need to be the same dimensions. You might find, as we get more advanced and we're importing data, that sometimes things are imported as columns and you want them as rows. You want to be consistent. Maybe you have your variable defined that is your time course, and you have a variable defined that is the results of your time course. So one is all your time points and the other is the actual outputs. And perhaps one of them is a column and one of them is a row, and you're trying to add these together. So there is a transpose operation to allow you to convert from one to the other. So if I look what's in my var, it's a row vector. It's going across. If I do my var equals my var and then put this little single quote at the end, it's now transposed it to be a vertical column vector rather than a row vector. So this single quote at the end of a line means transpose. And that will spin the matrix from a column to a row, and it will also take it back again. So that's useful when you find you've actually got something the wrong way round, you're finding your dimensions don't agree, check the dimensions and check if you need to convert one of them from columns to rows with the transpose operator.